Okay, I'd like to talk a little bit about cell diagrams and standard reduction potential tables. If we go back to our original diagram over here, what we mentioned was that zinc was undergoing oxidation and copper was undergoing, or copper 2 plus was undergoing reduction. Instead of drawing that full cell diagram with all those beakers and the electrodes and everything, you can express it in terms of this kind of abbreviated type cell diagram. And what you do is on the left side you always put whatever's undergoing oxidation. Now it doesn't matter about the order of these because we always know that the oxidation will be on this side. Then you've got the double line which represents the salt bridge, and then you've got whatever's going on in the other beaker with the reduction. And again, it doesn't matter about the order of these either. So if we wanted to find the voltage or the potential from the table, because we know that we've got electrons going through that wire and there's going to be a voltage associated with that, what we do is we use a standard reduction potential table. And if we go and take a look at the table, here's what we notice. It's called a standard electrode reduction potential table because everything on here is a reduction. If you remember what I was saying earlier, I said that anytime you've got electrodes on the left side of a reaction, it means that electrons on the left side, it means electrons are being gained, and that means reduction is occurring. These are all reduction potentials because all these reactions are reductions. Now you'll notice that they can be positive or they can be negative, and that the one that involves hydrogen here, 2H plus, giving hydrogen, is set arbitrarily at 0. So that's kind of just our arbitrary set point, and everything is relative to what we call the standard hydrogen electrode, and that's it right there. Alright, so we've got all those and all those values. How do we handle them? Okay, well we've got over here, we've got zinc and zinc 2 plus. So what I do is I hunt down values in here that have both zinc and zinc 2 plus. So every species I have over here must be in the standard reduction potential reaction that I choose. So if I'm looking for zinc and zinc 2 plus, this is the one I'm going to pick, and I see it's negative 0.763 volts. That's the one for zinc and zinc 2 plus. I call that E0. That's a standard reduction potential. Now I've got to hunt down one that involves copper 2 plus and copper. So I do that and I find that's this one up here, copper 2 plus and copper. I just copy that reaction down. That's what I did here. Now keep in mind there's some other copper reactions around here too. There's a copper plus here and copper, but that one's not going to cut it. It needs to be copper 2 plus. So when you're looking at these, make sure you pick the right reaction, the one that involves all the species that you're looking for. Now in these cell diagrams you're not going to show water generally, so you shouldn't be looking for that. But everything else should be pretty much mentioned in their cell diagram. Now what we're going to do is we're going to see if we can calculate the voltage that is being given by the cell. Now what we do first is, knowing that this is supposed to be an oxidation and that everything that I've taken off the reduction potential table is a reduction, I know that I'm going to have to change this into an oxidation process. And the way I can do that is to flip the reaction. Now if I flip the reaction, I have to flip the sign of the voltage as well. So that's what I've done here, is I've taken the first reaction and I flipped it, and when I flipped it I also flipped the voltage from minus 0.763 volts to plus 0.763 volts. If it's necessary to multiply the reaction, and it may be necessary to do so if these electrons are different because we're going to have to make those electrons equal, we do not multiply the voltage. Now the reason for this is because potential is an intrinsic property. Now an intrinsic property is a property that doesn't change depending upon the amount of something that you have. Other intrinsic properties that we know of include color, and you know that if you've got a kilogram of copper sulfate, it's blue. 10 grams of copper sulfate is still blue, so the color doesn't depend on the amount you have. Density doesn't depend on the amount you have. Melting point, boiling point, lots of other things that don't depend on the amount you have of the material. This is as opposed to an extrinsic property. Extrinsic properties depend on the amount you have, and there are lots of common ones you can think of, like volume and mass and length. All those depend on how much you have of the compound. But potential is not one of those. It's an intrinsic property, which means when you multiply any of these reactions, you don't multiply the reduction potential. You leave that the way it is. Alright, so we flip this one. We leave this one the way it is because it's still a reduction. Now we can go ahead and add the reactions together, and that gives us our total reaction of the cell. And we just add these together now, and that gives us our E0 cell value. So this would be the voltage that would be released by the cell, or it's called a cell potential. The other thing we can possibly find is once we have a cell potential, there's a relationship to delta G0, and that is through the equation negative NF E0 cell. So we can use this E0 cell value here. And the N is the number of electrons transferred in the balanced reaction. And in this case, 2 electrons got transferred. We got 2 electrons here, 2 electrons here. And that becomes N. F is called the Faraday constant, and it has a value of 96485 joules per volt per mole. But a joules per volt is also equivalent to a coulomb, which is a measure of charge. We'll talk a little bit more about that later. And of course, E0 cell is a cell potential. Now, if we wanted our value of delta G0 in kilojoules, then we would do a conversion at the end. So we do minus 2, that's for the number of electrons, 96485 joules per volt per mole, times 1.103 volts, that's what we've got up here, and then a conversion into kilojoules at the end, and this comes out to minus 212.8 kilojoules per mole. What we'll see later is that for spontaneous electrochemical processes, the E0 cell will always be positive, and as you can see, if we have a positive E0 cell, that's going to make the delta G0 negative because the N will always be positive and F will always be positive. I'll give you a summary of the consequences of the signs of values a little bit later, but this will serve as an introduction to electrochemical cells and cell potentials.